Hello everyone, stars form by the gravitational collapse of molecular clouds, also known as stellar nursery, in the interstellar space. And they die? Well, that depends upon the mass of the star. But what does it mean for a star to die? The thing is that a star dies, but it cannot continue the process of nuclear fusion. And when the star dies, it forms, depending on the mass of the star, either a black hole, neutron star, or a white dwarf. Now if you think about that, stars are massive, and because of that, they have strong gravity, and the gravitational force is continuously trying to compress the star. A star remains stable or in hydrostatic equilibrium only because of the nuclear fusion that is happening in the star. Hydrostatic equilibrium just means the state of balance between a force, such as gravity, and a pressure gradient force. When the star is alive, the force of gravity is counteracted by the pressure gradient force generated due to the process of nuclear fusion inside the core of the star. Once the nuclear fusion in the star stops, there is nothing to resist the collapse of the star due to the force of gravity, and the star starts to collapse. For a star with a mass of less than 8 solar masses, after collapse it forms a white dwarf. Now the thing that is very interesting is that there is no fusion happening in the white dwarf. So what actually is counteracting the force of gravity now? It turns out the answer to this comes down to a fundamental principle of quantum mechanics, the Pauli Exclusion principle. To understand the Pauli exclusion principle, we need to understand the standard model of particle physics. Standard model of particle physics is a theory describing all of the known matter particles and 3 of the 4 fundamental forces of nature. Standard model, however, does not describe gravity. In the standard model, there are 2 types of particles, namely fermions and bosons. Fermions are particles with half integer spin, and bosons are particles with integer spin. So what actually is a spin? Spin is a kind of an intrinsic angular momentum these particles have without actually spinning, or in other words, they have properties as if they are spinning without actually spinning. All of the matter in the universe is composed of fermions, and all of the forces in the universe is mediated by bosons. Fermions themselves are divided into 2 groups, quarks and leptons. There are 6 types of quarks, up, down, strange, charm, top, and bottom, and 6 types of leptons, electron, muon, tau, electron neutrino, muon neutrino, and tau neutrino. The difference between quarks and leptons is that quarks can interact with the strong nuclear force while leptons cannot. Now bosons and fermions, because they are different by their spin, are also different in many other ways. Fermions obey Fermi-Dirac statistics, whereas bosons obey Bose-Einstein statistics. Now let's talk about the Pauli exclusion principle. The Pauli exclusion principle states that 2 or more identical fermions cannot occupy the same quantum state within a quantum system. It happens because the total wave function describing 2 or more identical fermions is antisymmetric, whereas for bosons it is symmetric. That means if there are 2 fermions, such as a pair of electrons, and you swap their positions, the total wave function describing the system will swap sign, whereas for bosons, the wave function will not change. Now, if 2 identical fermions are in the same state, for example, electrons in an atom with all 4 quantum numbers being exactly the same, there wouldn't be any change in the total wave function of the pair of electrons as we swap their positions. But as we said, the total wave functions of the electrons should swap sign as they are fermions. Thus, such a quantum system where the wave function is not antisymmetric is not possible if the 2 fermions are identical. Pauli exclusion principle is the reason of why there can't be more than 2 electrons in the first orbit of any atom. The 2 electrons have opposite spins. That's why they can be distinguishable from each other, or in other words, they have antisymmetric wave function. But if we add another electron in the first orbit, the spin of 2 of the 3 electrons should be the same, and the other quantum numbers are also the same. Thus in this case, the Pauli exclusion principle would have been violated. Thus there can't be more than 2 electrons in the first orbit of any atom. Matter takes up space actually comes from Pauli exclusion principle acting on these particles and preventing them to occupy the same quantum state. Now let's come back to stars. Why don't white dwarfs collapse further? The thing is that as gravity tries to collapse the star further, there comes a point when an apparent force due to the tendency of electrons to not occupy same quantum state due to the Pauli exclusion principle causes the kind of repulsive pressure to generate between electrons in the star. This pressure resists electrons to come closer and is known as electron degeneracy pressure. And this pressure is what causes the outward force to counteract the force of gravity. Thus the star stops to collapse. The hydrostatic equilibrium gets restored. In neutron stars, the story is a little different. Gravity initially wins and is able to compress the star enough for electron capture to begin. In electron capture, the innermost electron of the atom gets captured by the nucleus. The electron then reacts with one of the protons of the nucleus, forming a neutron and a neutrino in the process. This happens in large scale inside neutron stars. Eventually, most of the star is just made up of neutrons, which justifies the naming of the star after it. So in a neutron star, it's not the electrons which causes degeneracy pressure, but neutrons, as they're also made up of fermions, up and down quark. Now I hope you got the answers to why white dwarfs or neutron stars don't collapse to form black holes. If you have something to ask, you can ask in the comments. Thanks for watching, see you next time. Bye.